In the programming community, there is a huge discourse about which technology is the best. But you know what? They all suck. That's why I've decided to throw them all in the garbage and design a custom CPU from scratch. You know, like a real programmer. Before doing any work, though, I had to do some research. I watched a few episodes of Ben Eater's Breadboard CPU series and also finally finished Nun Game to get up to speed. Then I opened VS Code and started writing the design doc of the CPU. The first version of the CPU had a 16-bit word width and a 12-bit address space, which basically means 4 kilobytes of RAM, 2 registers and the von Neumann architecture. It also had 11 instructions, notably these. You can see 4 instructions for manipulating data, some arithmetical logical instructions, a jump and a conditional instruction. Then I had to actually implement them. You see, the computer doesn't actually understand what LDA means, so you have to explicitly guide it to understanding. Now that I'm saying it, it sounds extremely motivational, but never mind. You have to explicitly tell it to take the address provided as argument and give it to the memory, and to then take the memory output and load it into A. This part of the computer is called the control unit, and these commands are the microcode. This entire process is also a part of something called the fetch, decode, execute process, but explaining that is drastically out of scope of this video. Anyways, after having done that for the entire instruction set architecture, I actually had to design this thing. I was using a program called Logisim because I'm too dumb for VHDL. This process wasn't very notable, maybe apart of the fact that I had to write a simple Python script to convert human readable microcode into its binary representation, but whatever. But now I can actually show you how the instruction cycle of LDA looks, for instance. That ain't particularly exciting, I know, but now the CPU actually works, so let's run a few programs, shall we? This program calculates the Fibonacci series, as you can see down there in the memory. And to test the conditional jump, I programmed the multiplication program. As you can see, it multiplied 5 by 4 into hex 14, which is 20 in decimal. That's cool and all, but this CPU does have a few issues. First of all, there is no input and output. Furthermore, the instruction architecture is still pretty limited, making programming in it extremely painful, which is not helped by the fact that no assembler really exists, so I have to write everything in machine language. So it's time to take all of my hard work and put it in the garbage, where it belongs. Well, not completely. The first 11 instructions of the new CPU are essentially the same, except the jump instruction uses the flex register instead of just A. I also added the stack, which makes functions possible. At last, I added the ext instruction. It basically serves as a prefix that doubles the number of possible instructions. To the extended ISA, I added immediate addressing and the index register, which basically offsets the value on the bus by some set value. I also added a 16 by 16 display, which is bound on the addresses FF0 to FFF, and 4 buttons bound on FEF. Their values are gathered with polling, which basically means to start a loop, handle buttons, and execute the rest of the program logic and restart the loop. And all of that is great, but to make programming the computer actually viable, I had to write an assembler. My assembler was written in Python, and it kinda sucks. It was written in a sleep-deprived Friday coding session with really messy code. It also doesn't have normie shit like macros or imports, but it does support basic instructions, labels, and the .w and the .org directives. So, as Todd Howard would say, and it's still less awful than JavaScript, though that ain't a big feat. But enough with that, cause it's time to write some programs. I rewrote the Fibonacci and multiplication programs from earlier, but since we have a pretty assembler, we can write something cooler too. So I started writing a game. And after all those hours curled up at the computer like some sort of gremlin, debugging misplaced wires, I was really excited. Yet I don't have that much to show here, as, explaining assembly ain't that fun. I can say, though, that the game is basically a scuffed Chrome Dino game with the dino being replaced with Amogus and the only cactus looping around the screen in a continuous constant interval. Here is the game, in the flesh. As you can see, you can jump and you can die, which is all you need for happiness, I think. Yeah, this is all I got. It's not very practical or well designed, but it was still fun, I guess. I don't know. If you want to try programming it for some reason, I'll probably upload the assembler and the project file on GitHub, so feel free to clone it. Just be worried that the assembler outputs the code not as a binary, but as this weird text file format that you can upload in Logisim. Okay, that's really all, bye. Also sorry for my 4 months hiatus. I have to study for Maturita, which I need to pass to graduate high school in the Czech Republic.